Welcome back. In this video, I'm going to be discussing how to solve what I'm going to call rendezvous problems. This is where you have two objects. They start from not necessarily the same place, but eventually, after some time, they meet. That's why I'm calling them rendezvous problems. So I'm going to solve three problems in this video. This is the first problem, and it's question 3.3 that we are going to be interested in. I had to include all of this detail only because it was in the question, and I need this detail as well as this, but we're not interested in all of this for now. Okay, so let's jump right in. So we see that we have a ball A is projected vertically upwards at a velocity of 16 meters per second from the ground, and we can ignore the effects of air resistance, and we're going to use the ground as the zero reference. Okay, so ball A starts flying, and they give us the details for that. And then 1 second after ball A is projected upwards, a second ball B is thrown vertically downwards at a velocity of 9 meters per second from a balcony 30 meters above the ground. We can use this diagram. And the question is, calculate how high above the ground ball A will be at the instant that the two balls pass each other. Now, the first thing that I have to say is that the method that I'm going to demonstrate in this video works for problems of the following type. You need to have two objects that meet. You don't know where they meet or when they meet. So that's fairly complicated because there are, of course, two things that you don't know here. If you know one of them, then the problem is not that complicated, and you don't need the technique that I'm going to demonstrate here. So before you start writing out some of the key equation that I'm going to show you, just make sure, is this problem of the type that I described? Is it the case that you don't know where your objects meet or when? Okay, so as always, in order to solve this problem, we need to take the situation that we have and we need to express it mathematically. So to say that two objects meet, you can use an example for when you meet with your friends. What do you need to do in order to meet with someone? You need to agree on a place where you meet, and you need to agree on a time. That is, you need to be in the same place at the same time. And those are the equations that we're going to write down now. So I have two objects, A and B, or they're called A and B in this problem, and I'm going to say that A meets B. That is to say that the final position of A is the same as the final position of B. Okay, so that's a fairly simple thing to say, but what does it mean? Now, here's the thing: we don't have equations explicitly for final position. we have a number of equations. In fact, all of our equations involve a delta x, a displacement, which is a change in position. So let's start out by showing how we can use displacement to get final position. And of course, to do that, we just look at the definition. What is displacement? Displacement is final position minus initial position. So in this equation here, this is going to be our key equation. In this equation, we're talking about final position. So that means that I should try and isolate the final position in this equation here. And to isolate the final position, I need to get rid of this term here. At the initial position, I need to move it across to the other side. To do so, I add initial position to both sides. Right, so I have a minus xi plus xi. They will cancel, leaving me just with, I will only have final position on the right hand side. Or if I try and write this a little bit better, or make it more readable, I have that the final position is equal to the initial position plus the change in position of whatever object I have. So now I'm going to try and express this equation star a little bit. Well, I'm going to use this this line that I've just written out. So then the final position, I can say that the final position of A is just the initial position of A plus the displacement of A. And similarly, the final position of B is the initial position of B plus the displacement of B. So now I have an expression for x final A and x final B. It's this and this. Right, so I'm going to just take these expressions and I'm going to substitute them into this equation here. Let me first write out that equation again. X final A equals x final B, and x final A is this. So I can write x initial A plus the displacement of A, and that is equal to the initial position of B plus the change in position of B. Okay, so we now need to ask ourselves, what equation of motion can we use for the displacement? Right? Because I did mention we have equations of motion for that. The initial positions of A and B, for that we don't need any equation of motion. The initial position of A, well, it's the ground, and they told us use the ground as zero reference. So initial position of A is just 0. And if we say that up is positive, then we get higher, or the position increases going up. So the initial position of B is 30 meters. So we don't need any equation of motion for xia or xib. We're going to need an equation of motion for the displacement of A and B. So what do we know about A and B? We know an initial velocity. It's either 16 or 9 meters per second, up or down. So we need an equation that has initial velocity in it. of course, we know our acceleration is 9.8 meters per square second downwards. And we say we're going to take up to be positive, so this is going to be, in our equation, we're going to write minus 9.8. And then we know something about the times. We know the relationship between the time for A and the time for B. So if you have a think, what equation has initial velocity, acceleration, and time, as well as displacement? Because of course we need an equation to represent the displacement. And if you think which equation of motion has all four of these variables, you'll come up with the following. That the displacement of an object is its initial position multiplied by the time of flight plus 1/2 a time of flight squared. So we're going to use this equation now to write an expression for the displacement of A as well as the displacement of B. So let's do that now. I'm rewriting this equation. So I have the initial position of A, that's not going to change, plus, now in place of delta XA, which I have here, I'm going to write this. It's the initial velocity of A times the time for A plus 1/2 the acceleration times the time for A squared. So this is, what I've just done is I've written an alternate expression for what I've just highlighted. And in particular, this thing I said is all of this. And now I'm going to do the same thing on the other side over here. So initial position of B, that doesn't change, plus, now I use my equation, VI, the initial velocity of B, times the time for B, plus 1/2 times the acceleration times the time for B squared. Again, all I'm doing is I'm subbing in, I'm rewriting this thing that I've just highlighted. The initial position of B, that's what I've got here. And I've written the displacement of B, that's all of this thing. That's this thing here, for which I use this equation. Okay, so now that I've done that, I'm going to start substituting in, and you're going to quickly realize that there's an issue with the times, and we're going to get to that in a second. But I just, for concreteness sake, I just want to I want to move away from the abstract as quickly as possible because I don't want to lose anyone. So let's start over here. The initial position of A, what did we say that was? We said it was 0. Let's just remind ourselves, what are we trying to do? We're trying to figure out where they meet, calculate how high above the ground ball A will be at the instant the two balls pass each other. Okay, so they're going to pass each other somewhere, we're not sure exactly where, and that's what we're trying to calculate. So we said the initial position of A is 0 plus, remember, up is positive. Now the initial velocity of A was 16 meters per second. Because we're saying up is positive, that's positive 16. multiplied by the time for A plus 1/2. Now minus 9.8 because up is positive times the time for A squared. Okay, now let's look. What is the initial position of B? It's 30 meters. 30 meters above the ground, hence positive 30. Plus, now, what is the initial velocity of B? It's 9 meters per second. The initial velocity of B is 9 meters per second down. And since we're saying that up is positive, we need to write minus 9 times the time for B now, plus 1/2, again minus 9.8. Times the time for B squared. Okay, so let's have a look at this equation. We'll realize there are two variables, time for A and time for B. But we do know that there is a relationship between the time for A and B. It has been mentioned that A started flying first. A is projected vertically upwards at a velocity of 16 meters per second. There we have it. And then they mention over here, 1 second after ball A is projected upwards, a second ball B is thrown vertically downwards at a velocity of 9 meters per second. Okay, now I need to illustrate this. So I'm going to draw a timeline. This timeline, this first one will be for A. Let's say that A, first of all, this timeline, off this timeline we can read times like, for instance, if it's 5 o'clock, 5 hours, 0 minutes, and 3 seconds after midnight. We can read a time off like that, and then a little while later, let's say 10 seconds later, we would read this time. So that's what I mean by a timeline for A. So we can mark off, we'll be able to mark off different events along the time, different events that apply to A. So let's say that A starts flying over here. This is the start. The start of A's journey occurs at this time. And then this is the end, or well, as far as we're concerned, this is where they meet, where A meets B. So then the time interval represented by, or the time interval defined by these two times, this is delta t for A. So you could take this time over here, subtract of this time, that would give you delta TA. And now we're going to look at delta t for B. And I'm going to superimpose the times together. I will synchronize the time. So this here would be the start time for A. B is still going to be sitting on the balcony when at the time that A starts flying. Let's just check that. Yes, A is projected from the ground, and B is going to be from on the balcony still. So B is still waiting when A leaves. And then let's say that this is 1 second over here. That's 1 second. Then they still meet at this time. So this is where B starts, and then they meet at the same time. Then this interval here represents the time for B. So clearly, what I'm trying to get at is that the time for B is shorter than the time for A. By how much? Well, we can see that to find the time for B, you take this time and you subtract off the 1 second. So that is, time for B is the time for A minus 1. That's our second equation. That's what we need to simplify, well, not simplify this, but to make it solvable. So I'm going to copy this line. Paste it there. So this is the first equation. This is actually going to be the second equation. And I'll use the second equation to rewrite the first now. Anywhere where I see a time for B, I will get rid of it and put this in its place. So let's write 16 times the time for A plus 1/2 minus 9.8. Actually, you know what? Let's do a little bit of simplification now, because this equation is becoming an eyesore. So 1/2 times minus 9.8 is minus 4.9. So what I will write over here is minus 4.9 delta TA squared. That is equal to 30 minus 9 times, now we use the substitution, delta TA minus 1 plus, no, not plus, but again I'll use the simplification, minus 4.9 times delta TA minus 1 in brackets, the whole thing squared. Okay, so now I have an equation just in delta TA, and now if I simplify this equation, maybe I can solve it. So that's what I'll do. I'm going to leave the left hand side alone for now, because I can see that on the right hand side there's some work to do. I can multiply the minus 9 into the bracket, and if I do that I will get minus 9 delta TA but plus 9, and I have a bracket that I need to square. I'll first square the bracket and then I will multiply by, then I'll distribute the minus 4.9 into the bracket. The first I get delta TA squared, first one squared, minus twice the product of the two, plus last one squared, which is just going to give me 1. And now I'm going to rewrite my left hand side. It's very important to be cautious and deliberate, because we don't want to make a mistake with the arithmetic. Okay, so now minus 4.9, I multiply that into the bracket, I will get the first minus 4.9 delta TA squared. And then now minus 4.9 times minus 2 gives me positive 9.8 delta TA. And then minus 4.9 times positive 1 will give me minus 4.9. Okay, so we're getting there. So what kind of equation does this look like? Notice that you have a quadratic term here and another quadratic term here, but it's actually the same term. So those will cancel out, and so this will not be a quadratic equation. Besides that, you can see that the term of next highest order will be just all the terms in delta TA, and the order is 1. So this is going to be just a linear equation, or an equation of a polynomial equation of degree 1. So let's get all of the terms with delta TA on the left hand side, and we'll leave all of the constants on the right hand side, all of the numbers on the right hand side. So I have the 16 delta TA. I'm going to ignore the delta TA squared because remember they cancel. I've got this minus 9 here. I'm going to bring that across to the left, and I'll get positive 9 delta TA. And then I see I have something else here. It's 9.8 delta TA. And when I bring it across, I get minus 9.8 delta TA. And that is all. I don't have any other terms in delta TA. So now let's do the constants. I don't have any constants on the left. So I'll come to the right hand side. I just have the 30. And then I have a 9 plus 9. And I have a minus 4.9. Okay, so now I'm going to go to my calculator. And I'm going to simplify the left hand side. So I've got the term 16 delta TA plus 9 delta TA minus 9.8 delta TA. I can just add up the coefficients. 16 plus 9 minus 9.8. Let me actually write it like this. Factorize, in other words. If I do that, simply get 15.2 times delta TA. Okay, and on the right hand side, what do I get? I have 30 plus 9 minus 4.9, which is going to give me 34.1. And now, last step. The time delta TA is 34.1 divided by 15.2. Actually, I lied. It's not the last step. There's one thing we have to do beyond this. And we get 2.243 seconds. This is not my final answer. Okay, so what did we do? Let's recap. What's the question asking? It was calculate how high above the ground ball A will be at the instant that the two balls pass each other. So what we just found was how long it's going to take ball A to pass ball B. 2.243 seconds. So now that I know how long it takes A to do so, if I want to figure out how high it is, I can just take my time delta TA and I can back substitute it into this piece here. That'll give me the final position of A, and that's going to be equal to the height of A. So I'm going to write x final A is x initial A plus delta x A, and x initial A was 0 plus look, you don't need to write out this formula again. I'm just writing out this formula again because I want everyone to follow where I am. I don't want to lose anyone at any point. So this is how I get the final position of A, which is going to be the final height of A. Well, the height where they pass each other. So I get 0 plus the initial velocity of A was 16. I think it was 16. Yes, it was 16. So 16 times 2.243. This is minus 4.9 times 2.243 squared. And let's do the math. 16 times 2.243 minus 4.9 times 2.243 squared. That gives me 11.24 meters above ground. Okay, done. Let's just recap the critical part. So we said that in order to solve the problem, this was the main idea, that the final positions were the same, and we turned that into an equation that looked like this, which we further developed into this equation over here. And then we just said that there's a relationship between the times, and this yielded this monstrosity. Well, sorry, not that one. It's this one where we used the substitution. And then from there, we just needed to be careful, especially over here with the bracket when multiplying out the bracket. But that's just a bit of math. Just be deliberate, be careful, and you can solve. Okay, so I want to very quickly look at two more problems. In this one, a small disk C is thrown vertically upwards at a speed of 15 meters per second. By the way, this is from the 2022 supplementary paper. 2022 May, June, or 2022 supplementary. Okay, so, and this one, the one that we just did was, it was the projectile motion problem from November 2015. Okay, so now let's have a look. A small disk C is thrown vertically upwards at a speed of 15 meters per second from the edge of the roof of a building of height 30 meters. After half a second, a small ball B is shot vertically upwards from the foot of the building at a speed of 40 meters per second in order to hit disk C. If you hit something, you need to be in the same place as that thing. So over here, this is the question that we're going to be solving, the problem that we're going to be solving. Calculate the time from the moment the disk C was thrown upwards until the time ball B hits the disk. In other words, we're solving for a time very similar to what we just did. It's just we don't have to do the final step where we back substitute after finding our time and then to find the final height. Now, here's the thing. Again, we have two objects and they meet each other. We don't know where they meet. It's not given. It's not explicit. And we also don't know when they meet. In fact, that's what we're looking for. So it is, again, a problem of the same type that we just saw. So now I'm not going to explain how I got to that equation. I'm simply going to write out the key equation, which was that in fact, you know what, let me just write this first. The final position of, I want to put C over here. The final position of C is the same as the final position of B. And for that, I will write x initial for C plus delta x. C is equal to x initial B plus delta x B. And again, we have our initial velocities for both. We have our initial positions for both. And the time is a variable. So let me just state, I'm going to take up to be positive, so that initial position of C is 30 meters and the initial position of B is 0. So then I can write, I'm going to use now the equation for displacement. I'm going to use this equation for displacement to get expressions for delta xc and delta xb. So again, I write VIC delta t c plus 1/2 a delta t c squared. That is equal to x initial b plus VI b delta t b plus 1/2 a delta t b squared. And now I would like to substitute some values. What's the initial position of C? We said that's 30. The initial velocity of C is 15 meters per second upwards. Up is positive, so this is positive 15 times delta TC plus 1/2 times minus 9.8. Why minus? Because I said that I'm taking up to be positive. What's the initial position of B? The ground, which we said we would take as 0. Initial velocity of B is 40 meters per second upwards, so positive 40. Time for B plus 1/2, again minus 9.8 time B squared. And now let's go and write out the relationship between the times. So just like the previous problem, one of them starts flying sometime after the other, and it's ball B again who's flying a little bit later. Therefore, time for B is shorter than the time for C by 1/2 of a second. So we're going to use this equation now to make a substitution. I'm going to rewrite our equation like this. I leave delta TC alone. It's the time delta T b that has to change. One half minus 9.8 times open bracket delta TC minus 1/2 the whole thing squared. Okay, let's go and simplify this equation so that we can solve it. 30 plus 15 delta TC. Now 1/2 times minus 9.8 is minus 4,9 delta TC squared. Okay, now I'm going to distribute the 40 into the bracket. 40 times delta TC is 40 delta TC. 40 times 1/2 is minus 20. And now the half and minus 9.8, I'm going to put that as minus 4,9. But I'm first going to expand the bracket. The delta TC minus 1/2. So the first term is going to be delta TC squared minus twice the product of the two, which is just delta TC, plus the last one squared, which is going to give me 1/4. Let's write that as 0,25. And then the left hand side is not going to change for now. The right hand side I'm going to distribute into the bracket. Okay, so minus 4.9 times delta TC squared is going to give me minus 4,9 delta TC squared. Now minus 4,9 times minus delta TC is going to give me plus 4,9 delta T. What happened? Plus 4,9 delta TC. And now I have to take 1/4 of a funny number. What is 4 minus 4,9 times 0.25? I get 1 minus 1,225. Okay, so now let's stare at this equation to see what kind of equation we have. Again, I see some quadratic terms. This one and this one, but like the previous problem, it's the same term on either side of the equation, so they cancel out. This is not going to be quadratic, and so this is just a linear equation. I'm going to get all the letters on the left, the numbers on the right, and then solve. Okay, so the first letter on the left, I see, well, the first term with letters is the 15 delta T C, and then I have a 40 delta TC over here. When I bring it across, it's going to be negative. And I have this term over here, positive 4,9 delta TC on the right hand side, so negative on the left when I bring it across. And those seem to be all the terms in delta T. Okay, so now the numbers. Well, I have this 30. I'm going to bring that across. It's going to be negative 30. And then I have a negative 20 over here. And I have a negative 1,225. Okay. Now on the left hand side, I'm just going to add the coefficients. Like this. Okay. Now, the right hand side, there's nothing I can do besides just add up all those numbers. So what do I get? I get, what's negative 30 minus 20 minus 1,225. I get minus 51.225, and then on the left I have 15 minus 40 minus 4.9. That gives me minus 29.9 delta TC. Almost done. So delta TC is minus 51.225 over minus 29.9, which is going to give me I'm going to my calculator. I get 1,71 seconds. And there's one more thing that I need to mention. I realized I didn't mention why I made a certain choice. The question was asking for the time from the moment that C was thrown upwards. In other words, delta TC. That is why over here I chose to isolate delta TB instead of delta TC, so that here on the right hand side I could eliminate delta TC in favor of delta TB in favor for delta T, well, an expression in delta TC. That's why, I mean, you could have done it the other way around, but then when you get to the end after solving this long equation, then you still have to go back into whatever you wrote over here and solve for the other time. Okay, so that's that problem. Last one. This is a bit of a bonus. A ball X is thrown vertically upwards with a velocity of 5 meters per second from a height h. A second ball Y is thrown 1 second later vertically upwards at 25 meters per second from a height 20 meters below X. Calculate the time that elapses from the time that X was thrown for the balls to be in the same position as they pass each other. Okay, so again, we notice we don't know where they meet, we don't know when they meet either. So this is a problem of the same type. Now, just one thing. I don't like that they're talking about ball X, because, of course, I used X's liberally all over here. And I don't want to have two references to X, like one capital X and one lowercase x. So I'm going to do the following. Why can I not get rid of this thing? Okay, so I want to say let ball X be ball 1 and Y be ball 2. I'm not looking to confuse myself or anyone else. That's why I'm doing that. Let us now, of course, in those previous two problems, we had a picture. We haven't been given a picture now, so let's go and draw one. Ball X is thrown vertically upwards with a velocity of 5 meters per second from a height h. So let's say this is the height h over here. and then a second ball, so that's where ball 1 starts, and then from this height, and then let's say, I mean, we don't have to imagine a building, but I'm going to. So where was I? A second ball Y is thrown 1 second later vertically upwards at 25 meters per second from a height 20 meters below X. Actually, you know what? It might be a little bit confusing to imagine that this is a building. It's definitely not clear that Y is thrown from the ground, so let's just not make that assumption. So this is 20 meters. So if this here was height h, then this is at the level of h minus 20. This is where y, sorry, not y, object 2. This is where object 2 begins to fly from. And it goes at 25 meters per second this way, and then ball 1 was thrown at 5 meters per second that way. Okay, now let us solve this equation. So x final object 1 equals x final object 2, and x final is x initial. Let's write this a little bit better. X initial object 1 plus displacement object 1 equals x initial object 2 plus displacement object 2, and that is x initial object 1 plus, now I hope you are familiar with the equation by now, vi delta t, so I should have vi object 1 delta t object 1 plus half a delta t object 1 squared, that is x initial object 2 plus vi object 2 delta t object 2 plus 1 half a delta t object 2 squared. And then I make my substitutions. Okay, so you might think that we are in a little bit of a bind because we don't know what the initial positions are explicitly. I mean, we don't have a number. Not to worry. You have something about height h on both sides of the equation. The h's are going to cancel. Okay, so the initial position of object 1 was h. Again, I want to say up is positive. So I have initial position object 1 is h plus. Now, initial velocity object 1 was positive 5 meters per second, delta t 1 plus 1 half minus 9,8 delta t object 1 squared equals initial position of object 2 is h minus 20 meters below h, plus, now initial velocity object 2 is positive 25 meters per second, because I'm saying that up is positive. There's no square. There is no square on this time. It is simply the time for object 2. Plus 1 half minus 9,8 delta t for object 2 squared. Okay, now we need to take into account the times. It is given that object 2, that is ball y, flew later. So delta t for object 2 is shorter than delta t for object 1 by 1 second. 1 second. So now I'm going to go to my equation and I will make that substitution just like we did previously. And again, I'm going to call this minus 4,9 delta t object 1 squared equals h minus 20. I'm dropping the brackets, plus 25 open bracket delta t minus 1 close bracket plus, no, not plus, minus 4,9 delta t, sorry, I should have a bracket now, delta t 1 minus 1, the whole thing squared. I have h plus 5 delta t 1 minus 4,9 delta t 1 squared equals h minus 20. I distribute the 25 into the bracket and I'll get 25 delta t 1 minus 25, and then, ooh, almost mistake there. Now I'm going to multiply out my bracket first before I distribute. Delta t 1 squared minus twice the product of the 2 plus the last one squared. And now I'm going to rewrite the left hand side again. Honestly, I could have dropped the h. The h is a little bit well, a lot earlier. Okay, so now I'm going to distribute the 4.9 into the bracket. Minus 4,9 delta t 1 squared. Now, minus 4.9 times minus 2 delta t gives me plus 9,8 delta t 1. And then minus 4,9 times 1 is minus 4,9. Okay. So, again, we look at this equation. Sometimes you have to look at it for a little while. Try and figure out what is going on. We have quadratic term here and a quadratic term over here. Again, they cancel out. So to solve this equation, we're going to get letters on the left, numbers on the right, because it's a linear equation, right? Or polynomial of degree 1. So I see is a 5 delta t 1. I'm going to leave that on the left. The next term in delta t1 is this 25. It's positive on the right, so negative on the left. And then I see this term over here, positive 9.8 delta t1 on the right, negative on the left. And now I've been wanting to do this for so long. See this delta, this is h and h. We're cancelling them just like we did the quadratic terms, the minus 4,9 delta t1 squared on both sides. So we don't have to put the h's at all. Okay. Besides that, I have a negative 20 over here, a negative 25, and a negative 4,9. Need to give myself more space. So now we just need to add up everything. We do the right hand side first. Negative 20, negative 25, negative 4.9. What do you get? Negative 49,9. And on the right hand side, 5 minus 25 minus 9,8 all times delta t1, which gives us what? So what is 5 minus 25 minus 9.8? It's minus 29,8. So delta t1 simply minus 49,9 all over minus 29,8. This is going to give us 1,67 seconds. Okay, thank you for watching. Hope I've beaten this problem to death now, and you can smash all similar problems that come your way in similar fashion. Thank you.